Okay, let's start today's seminar. Today's speaker is Xiao-Gang from the National Taiwan University. So here to talk about the interesting topic, the enlightening dark photon with kinetic mixing. Please start when you're ready.
Okay, thank you. I think I came here 3 months ago. So thanks to Tianwan for asking me to give another talk here. Well, I'm passing by to the Taiwan meeting. But this talk I have not given many times, so maybe you have not heard my view about the dark photon. Okay, so the title is Enlighten dark photon with kinetic mixing. So I will explain the details of all this terminology. So I will talk about 4 different aspects. So how you make this kinetic mixing with U1 gauge groups. And now, of course, last year there was this famous W-axis problem showed up. So then maybe this kinetic mixing can it do something for that? And then I'll move to kinetic mixing. Usually people work with U1, 2 U1 gauge groups and then mix them together. And then actually, if you want to say, well, okay, so one U1 mixed with another non-abelian like SO2 or SO3 groups, how you do it, or even with 2 abelian groups, how do you do kinetic mixing? What are the difficulties? And then I'll talk moving into how you can get a CP violating kinetic mixing. Okay. Now, so this is why is it so small?
Maybe it's.
You can test your eyes.
Also, I sit close enough.
You sit close enough, but this is dark enough. We needed to. Yeah. Okay. So I will looking. So when we know we have this electromagnetism in our world. So it is described by a U1 even AM local gauge group. U1 AM, that's a Maxwell equation and satisfy all of this. But then somehow these days we talk about the dark world, dark side of the universe. Maybe there's some other U1 which work in some dark side of the universe. In that world, they have a U1 gauge group or working with each other. But then maybe there's no communication with us besides the gravitational effect. Well, in that case, most of the cases you don't care because you cannot communicate with us, so we don't care. But then, so somehow, if you can have some mixing between all photon with the dark order photon, then you may have some sort of connection, and then through this photon interaction, then you know something about the dark side of the world. Okay, but then how the dark world side of the world, how the dark photon interact with their interaction partners, maybe we don't know. But then through this type of mixing, then you may be able to get some information about it. Okay. But now, of course, you don't want to do it arbitrarily. You want to say, well, okay, maybe in gauge theories, there are some good principles. For example, this renormalizability is a good guideline. So you say, oh, okay, if I want to do something, I want to write my theory, which is renormalizable. Okay? So in that case, then you want to mix with this ordinary photon and the dark photon. You look at all type of interactions, and then you say, well, okay, well, I want renormalizable interactions. Then you find that this is the only one. If you start with this theory, that's the only one you can write. Okay, So then they say, well, okay, since this is such a simple theory, it's just 110, and you mix with thing. Then you say, well, okay, let's look at such a theory. What are the consequences? So if you do it, then because of this mixing, because originally they coupled to the dark side of the world, but then because of this mixing, and then you have some probability to turn into our ordinary photon, then we can observe the interaction. Then maybe you will be able to, through such interaction, to know the dark side of the world. So this is what people refer to kinetic mixing. Okay, so that's so that this explains the title. Through this kinetic mixing, then you might be able to find some information about the dark photon. Okay, so now having had this, then how this interaction will show up? And really, if you work with our standard model, okay. So if you talk about our standard model, then what you should work with is the standard model gauge group here, and then you have a U1 gauge group connected with the dark side of the universe. Then you ask how this dark side of the photon can mix with our U1 gauge group. Not only photon, but also Z. Also, you will find there's some interactions too. So now you just try to write the interaction of this guy as the kinetic energy for this dark photon, the hyper field U1Y, and this hypercharge gauge field has some interaction with its current. We know how to work out. You know the standard model. Then you just get how the hypercharge come to different fermions, other particles. And then maybe there's the dark side of the world. You have some interaction here. And then now the kinetic mixing become this thing, right? Become this thing. And then you not want to know. Well, this is, of course, is not the sort of canonical form you usually see when we define a gauge field. And usually you define a gauge field, you don't have this one, right? And then you do your quantization and all things. But then because of this here, maybe you want to first do something, diagonalization to remove this term, and then to redefine your fields. And so that then everything looks like a normal thing without the mixing. But then when you're doing that, it's not unique. They do know. So for example, you can define your dark photon, but then this dark photon that has some a little bit also mixing from the hypercharge. Then you also redefine your hyper or field this way. Then you find that your Lagrangian, the previous Lagrangian, can write into this form. So this is the diagonal. There's no mixing between y and x. But then, because doing this, then you have some shift the definition for y, and then this x has some component of this here. Okay, so this is one way you can do it. But then you can do another way. You say, I don't like this. I want to make this new x does not have mix with this dark side of the current does not have any new y interaction. But then this one has it. So you can define the y prime equal to y plus sigma nu, and then this one here. And then you say this is also the canonical form. So you find this. But then, of course, this is just a pure two-way ways of doing it. You can do the linear combination of these two, and then you can have basically infinity of a number of ways of doing it. Okay. So now the physical effect will be, say, well, if you're doing this way, you find that your new hyper field interaction with this one, just normalize the coupling constant. And then this one, you somehow through your Y field, so which contains the real photon and the Z, then you can see something about the dark world. Okay? But then this way you say, well, how come? And then I cannot see the dark world at all. Right. So, but then this is because this field and this field is a linear combination of them. But then the question becomes, hey, then which way is the so-called correct way? Okay. So the correct way. Before I do that, let's say, well, because we know this hyperfield is expressed in the standard model, photon and Z, and the W03 is a photon and the usual one. Okay, so if you do that, then you expand the previous thing. You don't not only have X and A mixing, but also Z and X mixed together. So then you should diagonalize this, remove this term, remove this term. Doing that, then you will modify this. For example, the A way I just showed corresponding to this old A expressed into the new A and the ZX, and the B way is in this sort of shape. So that the form looks different. Okay, so if it, so then you write the interaction into the new field. So this becomes the canonical form, this becomes the canonical, but then the interaction, looks different. Okay, so then the question is still, which one you choose to do it? Yes.
Sorry, one question. We start from the same Lagrangian. So
yes.
Those two redefinitions
Yeah.
do not make a physical difference, right? It's
That's right.
It's just a matter of convenience, which basis to work in.
Yes. Yes.
Okay.
Yeah. So, but then once you decide to choose one, then you should consistently use that one. But then, so this just the question. Sometimes people say, "Hey, what is a dark photon? Interaction with the dark matter or dark field, or not?" That's not the real definition. Then the definition is what is the physical consequences should come out of the same. So now, how do you do it?
Sorry, I think they're physically different, right? One is related to the hypercharge, the other one is the dark charge.
Yes.
So they are different.
They are different, but then the physical observables,
Yeah.
it should be not different. Right. So then you say, well, some interaction, I have this two field to interact, and then you do some scattering or do some measurement. Finally, I should get the same results. Right. So
I feel they're different. Anyway,
Yeah.
Please continue.
So how do you do it? Now, usually when you do this dark photon, probably dark photon has some mass. If that is the situation, then it's very easy to distinguish, to decide which one is the physical one. So this time you define your field by mass eigenstate. So then you will say, well, the physical, the dark photon has some finite mass. And then, of course, we know our photon does not have mass. So then you can define your dark photon and Z by the mass eigenstate. So 0, 1 is the photon, and the Z mass 1 is the Z, and some other mass 1 is the dark photon. So this way, then you don't have ambiguities. So, and then, of course, even with this one, so you say, well, maybe if I do this way, as I said, there's two ways you work consistently, you should get the same result. Yes. So if you work with the B way, then you will find that this one is already in this sort of mass state way. But then this one has the photon mixed up. Okay. So then one more way you say, well, okay, let's say this is the photon. This is a dark photon with a mass of mx, so it's this linear combination. And then the other one is is this A, it will have no interaction and no mass, so still no mass, so that's still the photon. And then this define the new field interaction with the different current. But then of course, then you say, what about if I work with this way? Somehow I didn't choose this one, but then you will find that if you're doing this way, this A has some mass, so you should rediagonalize it. You rediagonalize it, then the end result, you will end up with this one here. So then what you do is, then you say, well, okay, the mass eigenstate, I do this way, then I find there's a mixing between these two, but then you diagonalize it. This is the W mass, or the Z mass, this is the mass eigenstate, this is the X eigenstate, and then the Z photon is still massless. Okay, so this is how you get a physical correctly defined dark photon and Z. So working with this, people has done quite a lot of experimental search, because now it's very easy, because one is the mixed parameter. Here I use I downloaded some figure from literature. They use epsilon, so it's my sigma is there, and then this is a dark photon mass. So then you do all kinds of search, bin dump experiment, scattering, or decay experiment. Then you find a lot of parameter space has been ruled out, but then you have still some areas which are not excluded. In fact, particularly say if you have a heavy dark photon, and then this area has not been checked. So all kind of experiment now is trying to do the search. Now, because you do experiment, we have a difficulty to reach very low mass, very low mass. But then in this case, the cosmology has a lot of experiment observations that you can constrain the dark photon mass down to millivolt or even smaller. But then you notice that then these guys become very small. The copy also requires to be very small. Okay. Sorry.
What is the
Vertical. This is still the mixing. Mixing with some density assumption of the objects.
How much there are the dark photon in the universe? Just the particles show.
Yes, in some cases. So this is the dark photon. This is the dark. So this is dark matter. This is dark photon density. Yes, yeah. So it depends because then observation of cosmology say you are going through the media, then you have to assume certain sort of density. Then you can project out whatever the parameters. Okay. Yes. Well, there are several experiments that are new experiments trying to looking for dark photon mass and parameter. For example, in Shanghai Jiaotong University, that's where I'm now. They are looking at just like shooting some beam into some very thin foil, and then you kick out an electron. Maybe during the process you have a dark photon carry out some energy. Then you measure the final electron energy. If the energy conservation is working, then you say, okay, there's nothing happening. If the energy has some loss, then of course it requires a very high sensitivity. Then you say, well, there's something missing. So this is going on. At SLAC, there's a similar type of experiment they're trying. Okay. Now,
Sorry, what is the range they're looking at? Mass range.
mass range. So this is the MEV.
Capital M?
Yeah, capital M. So there is the MEV range. This covers some of the ranges in a previous figure. Some empty space are covering in some of this space. Okay, so yes.
Are there also light shining through walls experiments of this type? Converting in a way
Yeah.
the photon into a dark photon.
Yeah.
And you are now measuring very precisely energy loss.
Yeah.
In principle, if those photons interact very weakly, they can also penetrate the wall and you can reconvert them on the other side.
Yeah.
I'm just wondering what the relative sensitivity.
This you are referring to some searching for axion. So axion, you can have a photon coupling to axion. But then this is A does not have a two photon coupling. So that same type of going through the wall that doesn't work.
I'm referring to this principle one, not to those experiments.
Yeah.
Meaning, if you shoot in an electron, you scatter and produce a dark photon.
And then on the way, no,
And
the
on the other
to
side, you have some material you could reconvert. So it's the same kind of principle.
Yeah.
You're not
So-
using photon,
Yes.
but using the current direction.
Yes. There are some uses of this idea. In fact, so recently, NASA has observed a very high energy gamma thing. So they were wondering how that can happen. So then they say, well, the early universe, and somewhere very high density producing all this high energy photon, and then somehow they turn into the dark photon part, and then travel far away, and then come back again. Then we see such a high energy. That is some use. But then for laboratory, so the use of this idea, because of the parameter, I have shown something. It's too small. Too small. Okay.
Yes.
Bounce on epsilon is effect of the epsilon square. But to produce the particle and convert it back to
Yes.
traceable.
Yes, but here you need to measure an energy loss of the dark photons. You also have two dimensions, and you need to measure this. Energy loss very precisely.
Mm-hmm.
You don't have coupling. We understand you don't have an extra coupling square. You only
I thought you do, because in order to measure the energy recoil, you don't only need to produce it, you also need it to be
Yeah. So for this is say this if you have something that heated for you and produce an electron, and then electron coming heated this one, pick out the electron, and then in between something happen, then you emit a dark photon that's going away, and then you measure this. But then what you are saying probably is you have a photon come in and then oscillate into a dark photon and then oscillate back. That is all. But then that's the company is too small. Okay, so now I have the distinguishing them by mass. But then now suppose the dark photon is also massless. Then what do you do? Right? In that case, you don't have this sort of unique mass system to identify them. So in this case, then any sort of rotation between this are sort of a physical thing. So you don't know which one really to define as your photon or dark photon. Okay, but then again, come back to your question. Whatever your rotation you do, say you do any sort of rotation, the final result should be beta independent. Okay, so how do you do that in this case? So if you firstly you say, well, let's make a rotation and on top of one of the ways I already right, and then you rotate sine beta, and then the situation B previously corresponding to beta equal to 0. And then if the A, you present the beta equal to sigma cosine and W. So in this case, then you have a problem, which one really is the physical photon? So how do you get a result which is independent of beta? Okay. So this time, what you need to do is, see, we are caring about how the electromagnetic interaction is. So this side, we use some problem, maybe electron or something. And then finally, you detect it also using electromagnetic current. But then in between, because both are massless, you don't know actually is the A going through or X going through. So what you try to do is you include both effect. Both effect, then it turns out, so you exchange A in the previous case, you will get something, the original E, you get something like this, something like that. Now when you add them together, then you will find that you see this thing does not have a beta. Does not have a beta impedance. So then what you should do is you should really include both A and X all the way. Then you find the independent. What the result of introducing the mixing? So that means the sigma is not 0. Is basically to redefine your electrical charge. Redefine electrical charge. And then besides this, then you don't have if you only look at the standard model interactions, you don't have any other effect. The only thing is then you need to say really some dark side of the current Jx coming, and then you will see some different interactions like a milli charge or something. So this is I try to clarify this massless case. Okay. So now let me move into the spark photon kinetic mixing and the W mass anomaly thing. Okay. So now I think most all of you already know this W mass problem. CDF2 analyzes their data and find 7 sigma different compared with the so-called standard model or value which given by the PDG. So the number is this. Of course, this by itself, a lot of questions from my experiment side. But then here I say, well, let's take it to be true and let's see what happened. Okay, what happened? Then you need to explain this 7 sigma difference. Okay, so a lot of paper has been written since last April on this. So then about this correction, then the usual correction is the STU parameters. Okay, so you just do all this sort of calculation. And now, of course, if you have some non-trivial Higgs representation, which has a wave, and then you also modify this rho into this is the isospin and 3 hypercharge, and then you get something like this. Okay, so this for triplets, which Yungjing is an expert on the triplets Higgs contribution into this raw parameter, how it contributes to the STU parameters. So now, then let's say, well, what about the dark photon? Again, this is just give you the definitions of STU and how this raw parameter related to T parameters. Okay, so once you have that, then you say, okay, let me first work out. Now I'm assuming the dark photon has a mass, so then I know what to choose. For example, I choose the one I just chosen the case B, the way diagonalize it. you do this one here, and then of course I said you need to diagonalize the mass. Then you diagonalize the mass and get all this. And then next, you find this one will modify doing this. Then you'll find that the Z mass is modified. And this one here, the dark photon mass is defined by here. Then for us, this does not play a role for this S UT parameters. And then you just work out this one here. Okay. So now look at this. Then you can actually identify what is all these new interactions contribution to STU parameters. So all this dark current doesn't do anything because this STU parameter only involve the standard model interactions. So it's these guys. This one here has a modification, and you do that. So how do you do this? Well, it turned out a long time ago, London and Burgers, they had a paper. You can rewrite your modified Lagrangian in terms of modified Z mass, W mass, and the current is. Okay? So once you do this, then you compare with the STU parameter definitions. You will find that actually this S is related to here, this A parameter, C parameter, and the G parameter you find it here, and the U parameter you have A, B, C here. Now, because we already worked out all the details, how these guys interact with the photon Z. So this A, B, C, and the G parameters are already identified. So if you compare with the previous identified, in that case, the B is equal to 0, W is equal to 0, A is equal to 0, and then you find that C is equal to this one here related to the kinetic mixing, G kinetic mixing, and Z in mass is a shift, and then you can define the here. Okay, so once you have that, then you can get this STU parameter in terms of the dark photon mass, Z mass, and mixing in parameter. Okay. Actually, before this, there was a lot of confusing how you calculate the STU parameters for dark photon. There are a lot of papers did it not completed correctly. In fact, so we wrote a paper just last April after the W mass, I would say, how it works. We get this. And then it turns out Bob Holden, a long time ago, he also worked out similar result. But then his paper was completely buried in the literature. No one noticed. So after we wrote this here, and then Bob wrote, hey, I have done this 10 years ago. And I agree with you. So then we go back to check. Oh, indeed. We get the same result. So now, once you get this result, then you say you can study how the dark photon parameter affect the W mass. Right? Yeah.
This parameterization is very old.
Yeah.
And is useful for low energy. And now we have also high energy. We have this is for leg 1,
Yeah.
leg 2. So I mean, this STU is a very old thing. When we have only leg 1, and everything is low energy, and now you parameterize like this.
Yeah.
So I wonder, we now have leg 2, LHC will be data.
Yeah. In fact, we look at it.
So you have more observables.
So
this the photon entering there.
Yeah, but yes. Yeah, but then if you ask what is the contribution from the dark photon, and then this is the one. And then if you include the high A energy, the momentum, and the correction, and you have a STU, WZ, and all this, then we'll modify it. And for us, because the dark photon already is on shell, so then that's the result we have. But then if you say
modify the order, you say, okay, you can understand.
so,
There are orders, yes, and you say,
yeah,
you said they don't are not modified. Are
Yeah,
not
but not modifying in the STU parameter defined in the UU, in the more general. Yeah. Yeah. So, oh, sorry. Will not modify this definition. Yeah, because the
the
same.
definition, okay, but now the other observables,
Yeah, other observables we didn't start.
we measure very well.
Yeah. So in that case, maybe we should go back. So W.
The concept from the others, still, I think the concept from the others is much weaker than this. Usually in some cases. Even LHC measures some WG. The low pressure is reduced.
Termino, this is termino measurement. Experiment same in my case with W1, is W1 operator. Could be that doesn't end.
Yeah,
But is it terminal also? So we measure.
Yeah, so honestly, we didn't look into this because we thought maybe there was no measurement, but now maybe we'll go back to look at that again. So then you say, okay, so if I include this, how do I? Is there any chance this guy can fix the W mass problem? Don't consider other new physics. Just this. See what happen. And then it turns out to be very difficult. So if you want to bring to 1 sigma, you need a very low mass, 200 GeV. Well, dark photon 200 GeV actually, CMS has tried to look in that region. Okay, so this here is very sort of allowed. And then also you need a large sigma, so 0.2. So that means the modification is large. But then at a large dark photon mass, there's no much constraint from data yet. So then if you say, well, stay in this range, I can fix the W boson mass problem. Okay, but then this, if you CMS or Atlas continue to search their UCR data, maybe this will be ruled out. So if you separate looking for STU parameters, you see, well, there's some going up, some going down. The total effect coming to here to fix the W mass. So the message here is dark photon, if you have a large mass, has some chance to fix the W mass problem. But then with the CMS or Atlas continuing the data splitting, maybe rule out. So that is good because then this gives some momentum for them and to looking for further looking into the data.
Just to ask, are those monojet searches?
You say CMS.
Yes, are those monojet searches which can give?
Oh, I don't remember the details. But I think it's in the reference. Oh, okay, but it's in our the reference how the CMS work out the thing. But we just use the final result. Okay. So there's a chance. So now let me come back to this problem. How to work with non-abelian and group. Okay. So previously we have this U1 gauge group. It's just the U1, another U1, and then everything work out fine. There's a renormalized potential. But then if you say SU2, for example, then their gauge bosons is WA UU. Okay. And then you have a dark photon, maybe U1. So then there's an internal group index. It's open. So you cannot form gauge invariant, gauge symmetry group, symmetry invariant observable or tens. So then what do you need? Maybe some other field carry the same sort of a triplet. W is a triplet, right? So you to balance this to form gauge invariant terms. Okay, but then if you do that, then you find, well, maybe say for example we have a SU2 gauge boson W with some U1 group. Then you need, for example, a triplet, Higgs and Ton. You write it here, then you can balance it to form a singlet of gauge symmetry. But now, of course, see, previously I've been emphasizing renormalizability is a good thing to use. But then this here, you need a dimension 5 operator to do it. But then, in any case, then this shows a way, then you can do it. Okay, you can do it. Okay, so then when this, for example, triplet develop well, then you will have a W3 mu X mu mixing. Okay, so this is how you can realize actually non-abelian gauge group and U1 gauge group, the kinetic mixing. Well, in fact, in the standard model, people already done this, but then they didn't say in this way, actually it's a SU2 mixed with U1. In fact, people, you see this alpha parameter, okay, in the standard model calculation, actually there is a mixing between SU2 left and U1 Y or Y gauge group interaction. Well, in this case, then this triplet, where it comes from? It comes from the W, or the Higgs doublet, or then Higgs times Higgs dagger. Then you can have a hypercharge equal to 0, Y equal to the I equal to 1 or 3. So you take the 3 part, and then you can form a triplet. That's why I say it's something like this here, the standard model already have it. So once you have this, then you say, well, okay, actually it's easy to construct non-abelian gauge group mixing with the some U1 on Y gauge kinetic mixing. Okay, but then of course, naively you don't get a tree-level renormalizable contribution. But then at the loop level, you will get it. So then this is some sort of heuristic sort of diagram. So you have some new fermions come in, and then this triplet come to here, W come here, your Y come here, and then this has a valve, then you will do it. You'll do it. Okay. So you can do it. Then, if I'm greedy and say, well, I not only do this, I also want to CP violating kinetic mixing. Then what do I do? Okay, so this one, Y mu, X mu is a CP conserving. Then naively you say, well, okay, let's see, do a kinetic mixing with a CP violation. Then what you will do is just doing this Y mu, there's a tilt, right? So this one is a CP violation, okay? But then this turns out, if you write this one here, and this one is identical to something like this. And then you know totally divergent term in the Lagrangian does not have a perturbative effect. Of course, then you say, well, if I work with SU3 or SU2, maybe have a topological effect. But then for U1 gauge groups, you don't have this. Or at least you do perturbative calculation, you don't have this. So then, in order to have CP violating kinetic mixing, you also need to go do more. Okay. So now, what about what about this? Previously, I talked about non-abelian kinetic mixing. So I did this one, some triplets, some. If I read this, then this here is a non-trivial. Okay, But then, of course, if I just do this, then I still have the problem for what is it? Non-renormalizability. So I say, well, okay, you can do it, but then it's better. Maybe you can construct some renormalizable model which do the job. Okay. So now, before I go into a concrete model construction, then you just say, well, okay, so if I have this dimensional file operator, safety conserving, safety violating, I will be doing like this way. This is, for example, this is SU2 L. This is a triplet Y equal to 0, and this is some Montauk photon. Then you can get this. Okay, and then of course, if you allow this non-abelian mixing, you can also have the previously we discussed this abelian kinetic mixing. So you should consider them together. Then you expand it. Then you find the CP violating in the same turns out to be interaction with W plus W minus in this way. This then has some non-trivial or effect. So this is a triplet. Then you say, well, there's somewhere that mix the equivalent of kinetic mixing, just F and F X. Okay, so then you do that. Then of course the doublet Higgs, the triplet Higgs, the neutral ones has some mixing. You should include that also. Well, so then you say, well, what is the physical effect? Yeah, if you do something, there's no physical effect, and then you test it. So now we find that this one actually has the contribution to the electrical dipole moment of some formula. So this type of diagram, this type of diagram. This is some renormalizable model. I will come to that later. So you do this effective calculation, then you find that EDM is given by this one here, and if beta tilde is not equal to 0, then you have electrical dipole moment of Fermi. Okay, then of course, then you say, well, let's check the numbers come out to be okay. I haven't given the number. I'll give some numbers later. And another thing is, well, you may be looking for some other effect. So you're looking for TP collider, produce some X, and then because this here has a CP violating coupling, you can define some angular distributions. This is too complicated, but then just some angle which when this X come out, and then in some angles between this one and this gas, and then you define some angle larger and smaller. So you often see this forward, backward type of asymmetry. So this is equivalent to that. So you do that, but then it turns out we have searched the kind of larger parameter space. It's always very small. So our conclusion is this type of thing in the neutron EDM or electron EDM may be able to see some effect, not through this type of thing, but in principle you can do it. So now, how do you do a renormalizable model? So previously I just write on the effective operator dimension 5. You need a triplet to be there. So now how do I do a renormalizable model to generate some non-zero coupling? Well, it turns out if you have a type 3 seesaw, and then you have two generations. One of them has X, another them has a minus X. In order to have this anomaly cancellation, you need plus and minus to cancel, because these guys are chiral field. So you have X and something. Then once you have that, then you can have this one here. You going through all this heavy fermion triplet, heavy triplet. One of them has a positive, one of them has a negative. So you have these diagrams. So once you calculate all these diagrams, then you'll find that. Yeah, so F sum minus F. And if you want the 3 generations of heavy seesaw formula, you can make it 0. Okay. And then you completed the model, say, I also wanted the neutrino mixing to work. You need to introduce some Higgs doublets. But then that's not essential for this kinetic mixing part. So once you do that, then you'll find this beta CP violating, CP conserving in this particular model. And these two at one loop level, they are equal, coming down to this loop integral factor. Okay. And so you can try some number to say, well, make it close to experimental part or completed useless. So you say you find this one. If you take this degenerate case, but then if M12 is not equal to 0, CP violating will remain. So you find some number like this. So this delta is the phase of this M12, which is the origin of CP violation. But then there's no constraint, and you get something like this. Now, LHC has looked for type 3 seesaw fermions. They get some bound like 900 GeV. So you have to make it larger than 900 GeV to see what happened. And then this delta, CP violating is proportional sine theta, sine delta, and CP conserving is cosine and delta. And but this number is you don't know. Okay, then you say, well, let's say work out all the possible allowed range.
So why do we have these two mixing?
Oh.
Beta and beta tail?
Well, so when you have this automatically come into, see, these diagrams involve both, say, this one, the imaginary part, which produces the tilt, the real part produces beta. So this is automatically come together.
Sorry, again, IM13 is what?
IM13
IM13.
is the mass of so I have two of these guys. Okay, one is a positive one is a negative.
Okay.
So when you want the seesaw mass, you have this M12 allowed, and then this is there's a phase here. Okay, so the phase, if it's 0, it's CP conserving. It's another 0, CP violating. So if it's between, they should have beta and beta tilted both appear. So that's why one is proportional to sine theta phase of this one delta, and another one is cosine delta.
And then you also have a mixing between photon and X.
Yes, yeah. So,
You-
so then in principle you should include, and of course when you include it, then you have more parameters of space to play. If you don't, then maybe it's a less parameter. So the EDM now we can do this diagram calculation. So we have done this calculation, and then this come to the EDM. And so for effect, for example, electron EDM now experiment is less than 1.1 times 10 to the minus 29 ECM. So this is some mixing between this different Higgses. Then you can have some band and some band and here. Basically, what is you look at this picture, you say, well, somehow in some parameters, they can reach the current experimental power. Okay, so you can reach a current experiment. If you have more data available, then you run the parameter space. At some stage, then you say, well, this is too unrealistic, and then you give up this model. But then at this moment, essentially, the parameter space still allow such large EDM.
Is this the latest electron in the M-bound?
This one here. This
This is the latest one.
yeah, this is the one when we wrote a paper in middle of last year. So these are some change. I don't think that from last year there's a change. Yeah, so this is the number or the time we check. Well, of course, if you are really interested in the W mass thing, and then you have this new model, then you have a triplet Higgs introduced, and then you say, what is the triplet effect coming into here? And then of course, then the Y is equal to 0, right? In this one, and then this one has a web, and then you have this tree level contribution here, and then loop level you have this here. So then you include this, then well, easy the previous sort of I say almost be ruled out by CMS, but then there because then you can relax it by introduce more somehow this value is not too small, maybe a few GeV. This is still allowed, and then you can have a bigger parameter space for that. Yeah. See, the previous thing, you have more space to produce the W mass. Of course, then you talk about the triplet Higgs. Then I think Yungjing has his collaborator. They have wrote a paper before the W mass, right? But then you say, well, okay, so this guy's contributed to S2 parameter, and the tree level turned out for Y not equal to 0 is go to the wrong direction. So then you completely need the loop correction to do the job. Okay, but then still there are parameter space are allowed. See, this is the one we feed the W mass use the model parameter lambda 4 defined here, the doubly charged mass and the web. Then there are solutions. And most of the work was doing the S2 parameter fit first, and then translate it into the mass parameter, the public parameter. But actually, you could directly go to the model parameter, and then you still find the solution.
Sorry, sorry, you're saying that you said at the tree level, its correction is the wrong direction.
Yes.
But you said that at the loop level, it will come back?
Yeah, come back, and then there are parameter space which are okay with the data. But then, you know, the mass distribution around here currently is still allowed by all atlas the same data. But then maybe some other day, tomorrow, maybe they will say, oh, okay, we close this window. That's also interesting if they close the window. Yes.
In the EDM plot,
Yeah.
you take MX XPD. So this one. So, but you mentioned that double mass heavier than 0, so can you explain the WR?
Oh, this here will decouple. We don't want to say, well, you solve every problem. Other than I suspect that there are parameter spaces because W mass is a CP conserving quantities. So this here is a CP violating quantities coming here, which is small compared to what you required for W mass. So it should be okay.
Which constraint is preferred to explain double anomaly?
Oh, you mean to solve the W mass? What is the range of this? For example, so for example, these masses, right? But then in this model, the W mass solution does not depend on this. It depends on this. You can shift the W mass solution to the triplets y to Higgs parameter. So they can pretty much decouple. Except that you don't want this W mass, I mean, the value to be 0, which is both okay. And then you have loop contributions also. Yeah.
The contribution is dominant.
Well, in this case, because this go to the right side. So if you say, well, this one is 3 GeV or so, by itself, so more or less you can already solve the W mass. Yeah. Okay, so basically here I have argued that to you, CPM-related kinetic mixing is possible to introduce. Maybe need to be careful. You don't want to get something 0 to start with. Then you need to go beyond the abelian kinetic mixing. You need an abelian kinetic mixing. And EDM is a possible test for this type of models. And W mass can be sort of accommodated. All right. Okay. So,
Sorry, I missed.
yeah.
So you're saying that to explain the W mass, you need a CP violation in the model,
No.
or they're independent?
They can be decoupled. Okay. Just say, well, I say because I do CPM, I need to have a triplet Higgs introduced. Then that one can help me to do the W mass. So you don't need to put them together. Okay, so I think I will finish my talking.
Thank you for the nice talk. Any questions?
The CP violating one of the observation. So it's on the loop function. F loop function.
Yes.
So it's depending on the momentum.
Yes. Yeah.
So this loop function have a momentum dependence. So how the loop function?
Yeah. So basically, it's here. It's here. So let me see. W. Yeah. So then, in the so then this one, that's the momentum. But then need to come back to the fermion. So here. So one of them is the photon, is on shell. Then the other one need to be off shell. So the calculation is involved. So they have to be careful to include the momentum into the total calculation. Yeah.
So they are like input parameter, be permanent.
No, you should integrate out. Because see, this momentum, right, basically is one of the px or pa is this momentum. When you do the integral, then you integrate from to the infinity, 0 to infinity. Yeah. Just like you do other loop calculations or the fixed momentum, you should integrate out.
Answer. Third, 0. What you say in the sentence? The third one by
Lower.
Yeah, that's right. This one by itself, you can check the So these guys, the momentum, yeah, sorry. Then is the momentum here, should include it.
third is
This one here. Then this one has the integration.
So my question is not for ADM equivalent effective coupling beta children. Beta children.
Better.
Beta tilde.
Yeah, so this is beta tilde is already.
But he's not discussing about the EDM. He's talking about something else.
No. This F function you're talking about. Yeah, so this one here you can keep it free before you apply to a specific processes. So the beta is dependent on whether this guy is offshore, onshore, or something. So basically it's this. Yeah, so you define this one here, then it's a beta dependent, P dependent, P square dependent. Yes. Yeah. So when you do a specific physical processes, then you attach it to, for example, EDM. Then you need to integrate the momentum. Yeah. Okay.
Any other question? I think we had many questions during the talk, so let's thank speaker again.
Okay. Thank you.
그 정도 이거 같은 경우.
Oh. So